break, and then 3 talks, and then we have another break, and then we have the 3 final talks of the day, so that we can breathe a bit between all these Zoom attending things. So the talks are recorded and live on YouTube. There is a Q&A section in Zoom where you can ask questions during the talk, and most probably we will summarize them at the end of the talk and ask the question at the end. And there is also a discussion session tomorrow at the end of the second session, if we need further discussion on one of the topics. And please feel free to provide topics you would like to discuss tomorrow as well. I think I stopped there for the introduction. I hope I didn't forget anything to say. And if it's okay, we can start right now with Subodip on probing patchy reionization using CMB anisotropies. And voilà. The floor or the line is with you.
Thank you very much, Marion and Adelaide, for inviting me for this talk. And it will be a real pleasure today to discuss about patchy reionization using CMB anisotropies. So I'll talk with you about what can you learn using CMB temperature fluctuations and polarization fluctuations on the reionization aspect, not only in the homogeneous part, which you usually deal with, but also the fluctuations in the reionization, in the electron density during the epoch of reionization. So reionization is an epoch which you all want to know, and there are several probes to it. We have 21 centimeter, we have CMB. CMB is a very powerful probe because it is useful to map the cosmic history from the surface of last scattering until now. So photons get scattered when it propagates from the surface of last scattering to us, and anything happening between that gets imprinted on the cosmic microwave background. And one of the interesting epoch of the universe is the epoch of reionization. And that's our central interest for this talk and this workshop. So I'm showing here the maps of the cosmic microwave background known to all of us, way from the Kobe WMAP to Planck. We have gone with better and better angular resolution and better sensitivity. In the future, the game is still on with going behind even better sensitivity with higher angular resolution. So the question now is, what new can we learn about the epoch of reionization using CMB signal? So before we start asking what we can learn, let us ask what are the open questions we have in the field. So these are the few of the questions which are interesting to me, and possibly some of them I have missed. The questions which still remains open is, when did reionization start? When did this process start? When did it end? Is it a fast process or a slow process? Are they driven by lighter halos or massive halos? How inhomogeneous is the reionization process? And if these are my open questions in the field, I would like to say, see what are my different probes from the CMB side which can shed light on these questions. So one of the most interesting probe which we are measuring for almost 3 decades now is the optical depth, the integrated electron density. It's a very powerful probe. It's the first measurement which is provided by several experiments. And here I'm showing you one of the key signature of the epoch of reionization on CMB photons is the reionization bump at low L, or at large angular scales, which is a very key signature of the epoch of reionization. You see this bump. But the problem is this is not a very powerful probe, because if I change my reionization history significantly, as you can see here for different colors, the observable remains nearly the same. So it's a very powerful probe to get to the value, the overall average value, but not to the very much to the details of the electron density as a function of redshift. Another important probe which you want to use is the kinetic Sunyaev of Zeldovich effect signal. So it is originating from the bulk motion of the electrons along our line of sight, and it induces a secondary anisotropy in the temperature field of cosmic microwave background at small angular scales or at large L. Here is again a plot from Planck collaboration 2016, where you can see that the signature of this power spectrum with respect to era 3000 at higher L is really flat. The one which is in cyan curve is the one which is coming from the late time after reionization is finished. So we call it homogeneous KZ effect. We have the effect from patchy deionization, that's in the dashed line. And you combine both of these, you get the red line here. And this is the reference model which is used. I'm going to talk today significantly about how picture can change in this plot with better understanding of the signatures of KZ in terms of the parameters of the epoch of reionization. And another interesting probe which is available to us is the B-mode polarization. And mainly we are talking about the secondary B-mode signal, which is generated when photons are propagating from the surface of large scattering to us. And it gets two distinct effects. One is called screening, which is important at small angular scales. And the other is called scattering, which is important at the large angular scales. So what is screening? Screening is happening because when universe is getting ionized, it never happens homogeneously, but it is significantly inhomogeneous. The electron density is significantly inhomogeneous. As a result, your average optical depth is not same, but it's having a fluctuation. So locally, if I have a polarization field, so there is a conversion from the pure E mode to B mode because of the fluctuation in the optical depth. And that gets imprinted in the polarization field of the cosmic microwave background. Another signature, which is interesting, is again a secondary anisotropy which gets induced in the B mode polarization, is due to the scattering effect. So the electrons around them sees a local quadrupole. And if there is a fluctuation in the electron density, then there is a net conversion to E mode and B mode polarization depending upon how much fluctuation is there in the electron density. So you can convert from the temperature to polarization depending upon how much fluctuation is there in the electron density. And it gets imprinted again in the B mode polarization signal, and we call it the scattering effect, which is important at large angular scales. So in very simple language, screening is something which is a conversion of power from the polarization to polarization, and scattering is a effect which is a conversion of power from temperature to polarization. So let's see now how these probes which I have are going to be useful to learn about the questions which I initially have shown to you. So let's say that I have these questions which relates to the parameter space of the epoch of reionization. And in another side, I have the probes which are available to me from CMB. We have the KZ signal, the B mode power spectrum, and the reionization bump. And in the remaining part of my talk, I'll tell you how these two sets can be connected, where you can think about the left-hand side as your lit parameters, which are related to the physical process of reionization, but we do not have direct handle to those. We want to infer those from observations. And right-hand side is my observable space. And the remaining talk, I'll be talking about how we can connect these two sectors. So to go forward with probing the epoch of reionization, let's ask, from whatever we know until now, that is optical depth, how well can we constrain the reionization history? So there are several models, as I have shown you before, and all of them can lead to the same effect. So we have chosen a fixed reionization history, as shown by this black line here. And here are different constraints coming from multiple observations. Taking this in face value, you can now ask, let us change a few parameters which are related to the parameter space of epoch of reionization, mainly the halo masses, which are driving the reionization. Is reionization a fast process or a slow process? And let us change these things and ask, what are the imprints of these in the on the CMB observables? So we make simulations of the different solar masses, halo masses of about 10⁸ solar mass to 10⁻10 solar mass, with a fixed reionization history. And as you can see just by eye, that the scenarios where I have a snapshot of the simulation for 10⁸ solar mass objects, with the minimum 10⁸ solar mass objects, you can see that the bubble sizes, these red patches here, are slightly smaller in comparison to the patches you would expect for a reionization driven by 10⁸ solar mass objects, which is significantly large. This means if I calculate the corresponding power spectrum of the electron density during the epoch of reionization, what you find is, with change in the minimum halo mass, which is driving the reionization, you get different amount of fluctuations in the electron density field. If the reionization is driven by lower halo masses, something like 10⁸ solar mass, just like blue curve over here, you can see that you can get something about a factor of 1.5 to 2 different in the amplitude of the RMS fluctuation, depending upon if you go from 10⁸ solar mass to something like 10⁸11 solar mass. So now the question is, what is the imprint of this effect in the CMB polarization and temperature field? So at first, I'll talk about the impact of this on the KZ power spectrum. So if we calculate the KZ power spectrum from the simulations, in the sense when you have a completely homogeneous scenario, which is not the case, but it's like let's ask what is the typical power you have, because in a homogeneous scenario during the epoch of reionization, that's the magenta curve which I'm showing here. In y-axis, I'm showing you the power spectrum, L into L plus 1 versus 2 pi times CL, and in x-axis, I'm showing you the multiples. So this is, you can see, this is the typical power you will expect during the epoch of reionization from a homogeneous, even if the reionization is driven by a homogeneous scenario, homogeneous electron density. Whereas if electron density is actually inhomogeneous, you would expect a much larger fluctuation, as you can see here, orders of magnitude difference, and they can differ by almost a factor of 2 to 3, depending upon whether the reionization is driven by lighter halos or massive halos. And this is in black dashed line, I'm showing you the comparison with the lens CMB. So let's take a deeper look into this problem and ask, what are the parameters which are affecting my power spectrum of KAC? So what we are doing here now is a signal from different simulations. So each of these boxes in the matrix diagram shows results from individual simulations for scenarios where your optical depth is like open 061 and open 054. In x-axis, you see for different values of the duration of the epoch of reionization. That's delta Z parameter. Delta Z is shown over here for delta Z1, delta Z2, and delta Z3. And for different minimum halo masses, which is driving the reionization in the y-axis. What you see is, you calculate the power spectrum at L of 3000, let's say, you see that when you move from lower delta Z to higher delta Z, your signal changes as expected. And also same thing happens if I keep the delta Z fixed, but I increase in the mass domain. So I can measure see a power spectrum from observation, and I just cannot say it is just because of large delta Z, or is it because of a large halo mass which is driving the reionization. It's a combination of both which affects you. And you can see there's a degeneracy in both this side. I can walk in the x-axis or I can walk in the y-axis. I can get similar effect. you get maximum effect, maximum power in the KZ when you have higher halo masses is driving the reionization, and also the delta Z is large. The trend is similar also for higher tau values, as you can see over here. That's not changing. So the main take-home message from this particular plot is that there is a significant degeneracy in between the parameters which are driving reionization, whether it's a larger or lighter or massive halos, what is the width of reionization, what is the typical mean value or the typical average tau value, and these are the parameters which are going to affect your signal of KC, and not only the delta Z parameter is usually think that is the case. Now the point is, if we want to compare this with observation, we cannot run a simulation every time. If we want to do a parameter estimation, we need a fast code which can do the parameter estimation and can easily explore the parameter space. So for that, what we have shown is that we can find a scaling relation to connect the power spectrum of KZ with the physical parameters of reionization. 3 for now, there can be more. We have explored 3 parameters. So here it is written in terms of the mean optical depth, tau, which one can actually measure from other CMB probes such as E-mode polarization, delta Z parameter, and this new parameter which you have introduced called the KZ bias parameter. This KZ bias parameter changes with the delta Z parameter, and this is what is shown in this plot, that how the KZ bias parameter changes with different minimum halo masses ranging from 10⁸ solar mass to something like 10⁻10 solar mass in blue to green. So what you can see that when your reionization is driven by heavier halos, you typically see the bias parameter larger than the scenario when it is driven by lighter halos. And now if you ask, using this fitting form, can we explore from current observation and forecast for the future of how this parameter space can be measured? So here I'm showing you a plot for tau, optical depth, delta Z, and the bias parameter measurement using SPT plus Planck observation. That's shown in red. And the forecast for Planck and ACT-POL SPT or Simons Observatory with its goal sensitivity, and Lightboard plus CMB S4 combination in magenta. What you can see here, usually what you plot or like to plot is the mean redshift of reionization and delta Z. That's only this part of the parameter space. But now there is a significant degeneracy between the delta Z and tau with the bias parameter. And we can then use this 3-parameter model to map the observed power spectrum of KZ with the parameter space of reionization, which are now delta Z, the mean value of the redshift of the tau, and the bias parameter. So this is all about KZ, that is the impact from the patchy reionization on KZ power spectrum. Of course, there are more signatures if you go to and ask about non-Gaussian effects, which I'm not talking today, but it's also very interesting. What about B-mode polarization? What is the impact on B-mode polarization because of patchy reionization? So from the simulations which I've shown you, from the same simulations, if you now calculate the B-mode power spectrum, secondary B-mode power spectrum, those are the results which are shown for different minimum halo masses in red to blue. So in blue, you are seeing for lighter masses. In red, you are seeing for heavier halo masses. So the one which is in dotted is the analytical because of the resolution limitation. We cannot go to very large scales. And these results are obtained from simulations. What you can see for tensor to scalar ratio of R of 5 times 10⁻⁴, if this is my usual signal I expect, shown in black, and this is my lensing signal after 50% delensing, what you find is that around L of 100 and above, depending upon your reionization history, the secondary B mode polarization can become important over the primary CMB. Of course, lensing is a contamination here, but this is the main signature which you would expect. The interesting part is that this typical scaling with L is typically fixed for different reionization history. But let's ask now again the same question: how this power spectrum of B mode, secondary B mode, depends on the parameter space, or like minimum halo mass and the width of reionization. Here I'm showing you the plot, again a similar plot with x-axis the width of reionization, the delta z parameter for different values of delta z, and in y-axis I'm showing you for different values of the minimum halo mass. Again, the trend is very similar as of KZ. As you increase the delta z parameter, the amount of power in the CLBB increases. And also, as the minimum halo mass increases, you again see a higher value of fluctuation in the B mode signal. This means the combination of both this sector, how big are the halos which are driving the reionization, and what is the typical width of reionization, that is going to regulate your power or the amount of fluctuation which is present in the CLBB power spectrum. The story is very similar. If you change tau, the overall conclusion doesn't change. So let's again get to a new scaling relation which you can use for parameter estimation from the upcoming CMB experiments. So here I'm showing you a way to constrain this, where again this is the mean optical depth tau, this is the delta z parameter, the width, and now I have introduced a new parameter called the bias parameter for B modes. As again you can see in y-axis the B mode power, the bias parameter, in x-axis the delta z parameter, and the trend is as you increases the minimum halo mass, you typically see higher bias parameter or more fluctuations in the B mode power spectrum than when it is driven by a lighter halos. So this particular quantity can now be measured from observations. One can now go to the observations from Simon's Observatory and CMB+4 and ask at what level we can measure this quantity and separate it from lensing signal and from the primordial B mode signal from gravitational waves. But one of the question is, before measuring it, will it be a big obstruction to the primordial gravitational signal? So the very simple answer to this question is not likely for the experiments which are going to be operational within next decade. So if you plot the typical bias you would expect on a value of r 2 times 10 to minus 3, that is my delta r, and compare that with the sigma r of the mission after doing a likelihood analysis, what you find is that for Lightbird-like mission, the bias can be much less than 0.5. Similar story for Simon's Observatory. I'm showing in magenta for scenarios where reionization is driven by 10⁸ solar mass objects. In red, when reionization is driven by 10⁻11 solar mass objects. For CMB+4, it can be a slightly big issue, about 0.5 to 0.8, depending upon reionization history. And for the futuristic proposals, such as PICO or a CMB Bharat, which is a CMB mission proposed to Indian Space Research Organization, you would expect a pop high bias because now your sigma is significantly small, and you could actually get completely shadowed by the secondary B mode signal because of reionization if R is really small, like something like 5 times 10⁻⁴ or so. So with this, I'll now tell you that I have shown you that how the parameter space of the epoch of reionization can be connected to the observable space of CMB, and by different simple scaling relations. And we are very hopeful, as I've shown you from the forecast from upcoming CMB experiments, that both this sector, the KZ power spectrum, the CLBB power are going to be very useful to actually address few of the questions which have not any handle yet. we will be able to tell you whether the reionization is driven by lighter halos or massive halos. We will be able to tell you what is the typical width of reionization. And by doing a joint estimation of both KSZ and BB signal, we can get a significant improvement in the parameter space. So with this, I'll now end my talk saying that with a few summary, that the epoch of reionization can be proved by the E-mode polarization, patchy KSZ and the secondary B-mode polarization, and cross correlations with other probes. Certainly, this is very interesting. The amplitude of the KSZ signal and the secondary B-mode polarizations are related to the duration of reionization, the optical depth, and the patchiness and electron density. And these are the parameter space which you can now explore using these signals. CMB missions can consider reionization history and patchiness during reionization with the help of upcoming missions such as Siemens Observatory and CMB+EOR. Significant development can also be done from ACTPOL. So we are also working on similar things now. And in future, 21 centimeter will be a very, very important probe to probe the typical bubble sizes. And doing cross correlations of CMB will be a very powerful tool. So the summary with my talk is, we are going to learn a lot about the physical process during the epoch of reionization from the upcoming CMB missions. We have a very bright future in this sector now. Thank you very much, and I will take questions now.
Thank you. There's at least one question on the Zoom, just about the definition of your delta Z. How do you define delta Z?
Oh, okay. Yeah, sorry about that. So it is mentioned from when the universe is 25% ionized to 75% ionized.
Okay.
That's the typical width which I mentioned. With the same region, we also define the bias parameter, and you can ask which is constrained with respect to the same seed of the initial conditions and the cold dark matter properties. So depending upon this width, some of the bias parameters or the results may slightly change, but not much.
And there's a second question. How well can you constrain different epochs of sources being the main source? Say mini halo at the early redshift, or macho at the intermediate stage, or high mass in the end stage? How could you differentiate the three? Yeah,
so let me rephrase the question slightly differently. Let me say at first, which part we are most susceptible, which part of the redshift we mainly see the effects from. So effects is, wait, I want to change my slide. Yeah, just give me a minute. So the main part of the reionization history which we probe is when universe is significantly ionized, about 40% and above. Even if some things are happening here, we really don't measure it well. Mm-hmm. So so the probe which we have explored, we typically see the imprint of in the observables like KSZ and the B-mode power spectrum. If there's a lot of change happening towards the end of reionization, this is the place which you can really measure very well. And depending where it is driven by lighter halos or massive halos, see, there's a beautiful connection. The connection comes from the fact that if I give you a fixed reionization history from the measurement of tau, which sets a typical value, I can now have a very larger halos, which is driving the reionization, much bigger bubbles, but my process has started significantly late because those halos has formed later in the universe. Mm-hmm. Whereas I can have a scenario where universe is driven by lighter halos, so I start fairly early, but it is very small patches throughout, so it looks pretty homogeneous, and the overall patchy power is less. So this is the two balance where you have to play with, and hopefully by using the KSZ power spectrum and B-mode power spectrum together, we can get a handle on the delta Z and the fluctuation in electron density. Okay, thank you. And just one quick question before moving on. What mass function is used in Gadget 2? In Gadget 2, so what we use is we use. I'm not very sure about this. So we use this Shed-Torment mass function for 2002, if I remember correctly. to get to the typical fraction of halos which are ionized at every redshift.
Okay. Let's say that we have one final question. Is when you did your forecast about S4, did you assume any delensing?
Yes, absolutely. We have assumed here about 70% delensing, if I remember correctly. But this can, if we go to more, sorry, if we go to more delensing, the impact will be even stronger.
Okay.
Yeah. So we can go up to 85% delensing. In that scenario, the impact will be even larger. Yeah.
Okay. Thank you very much. I think more in the chat or in the Slack. If there is more question, you can refer to the Slack and continue discussing on that.
Sure. Thank you very much.
Thank you. We have to move forward to the second talk by Eric Guzman, again of patchy reionization reconstruction using deep learning. If you can share your screen, then it should be okay.
Sure. Give me 1 second.
Sure.
There we go. Can everybody see that?
Yep.
Okay.
And can you put it on full screen? Sorry.
Oh, is it not on full screen? I thought it was. Oh, hang on. If I stop sharing, what if I just share my?
Yeah, perfect.
Yeah. Okay. Let me minimize this real quick. Okay, so thank you to the organizers for having me today. As mentioned, I'm Eric Guzman. I'm a fourth-year graduate student at Southern Methodist University. I'll be talking about patchy reionization reconstruction using deep learning. My talk today will be based on this on a paper that's currently on the archive over this topic. And so also thank you to Suvodeep for that great introduction. It provides the necessary background material for my presentation as well. So I can kind of skip some things. But upcoming ground-based CMB surveys will provide new high precision data. And as a result, new high precision data of primary and secondary CMB anisotropies. And as a result, we will need new analysis tools to replace the current suboptimal ones. And so machine learning techniques offer the ability to learn complex nonlinear relationships from data, which make them ideal for the construction of these new analysis tools. So today I'll talk about reconstructing patchy reionization in the presence of lensing using a deep learning network called RESUNET CMB. And so RESUNET CMB is a network that efficiently and simultaneously can reconstruct multiple distortion fields of the CMB, such as the lensing potential and the patchy tau, which is the variation of the optical depth. So that's what I'll talk about today. So as mentioned, I'll talk about two sources of secondary anisotropies, gravitational lensing and patchy reionization. Just as a quick review of gravitational lensing, mass between the observer and the surface of last scattering deflects incoming light, which is shown in this bottom left figure, where the CMB photons are traveling through the medium and the trajectories are being deflected. The deflection angle is given by this value here, where the gradient of phi, which is the lensing potential. And so gravitational lensing can convert E mode into B mode polarization, which can cause confusion in the search for primordial gravitational waves. So a good reconstruction of this phi value will allow us to properly de-lens the effect from the CMB, increasing our sensitivity in the search. For patchy reionization, today I'll only focus on the screening effect of the CMB fluctuations, which in this case, it spatially modulates the primary CMB anisotropies according to these equations, where e to the negative tau is what's modulating the anisotropies, and tau is again the optical depth, the variation of the optical depth. So the goal of the network that I'm going to present today would be to simultaneously reconstruct phi and tau, with the focus on tau, since the lensing signal is magnitudes greater than the patchy tau signal. And so to get a better understanding of what's actually happening, I'll show you the effects on the CMB. And so on the top, we have the effect of lensing, and on the bottom, the effect of the modulation by tau. And so on the right, we just have the primordial maps unlensed and modulated, and the lensing potential that we'll use to lens this field, and the tau map that we'll use to modulate this. So we go from unlensed to unmodulated. When we lens it, you should see a magnification and demagnification in certain spots according to this potential. And here you should see a difference in amplitude of the spots. So I go from unlensed and modulated to lens modulated. I go back and forth. You can see that some spots become bigger, some spots become smaller. Here, some spots become brighter, some become dimmer. So those are the effects on the CMB. So our network will try from these effects, we'll try to reconstruct these fields that are causing them. And so our network is a tool to go beyond the current standard method. And the current standard method for such reconstructions is the quadratic estimator, which is defined by this equation for the lensing potential, or in this case, the deflection field. And so the quadratic estimator creates an estimate of the distortion field by using products of observed CMB maps. So in this case, x and x prime would be your observed CMB maps. F is just a weighting function, and A is a overall normalization. And so tau and phi can both have a quadratic estimator of the same form, just with different weighting functions and slightly different normalization. But tau and phi, their quadratic estimates aren't totally independent of one another. A naive application of the tau estimator to these observed CMB maps would be biased by lensing. And so the quadratic estimator is a suboptimal solution. And so on the right here are some estimate is quite good. This is, with no.
If we lost you for a while. Oops. Yeah. Eric, are you back?
Am I?
Whoops. We lost completely Eric. Okay. Let's just wait for 1 minute to see if he's connecting again. Yep. We are all getting used to this online stuff, but unfortunately.
Maybe in the meantime, we can, there were a few extra questions for Subhadeep, so
Okay, fine.
If it's fine, if he's happy to answer them, maybe we can do that in the meantime.
Yep. Oh.
Am I back?
Oh, okay. Sorry.
Some brief internet interruption. Okay, so sorry, I'll do just a quick recap. So I'm not sure where I cut off, but hopefully you heard the explanation about the quadratic estimator suboptimal solution. So on the right, they were just examples of this. Let me actually lower this. There were just some examples of the true versus the estimates. You can see the tau estimate is still quite noisy, even with zero instrument noise. And so the goal is to create something that goes beyond this. And so ResUnet CMB is a convolutional neural network. So to understand what a convolutional neural network is, it's just a convolutional neural networks take images for input and are able to output a desired image or a classification result. So a simple kind of toy example that that's very common is this digit identification, where you input an image, it goes through these blocks, which are convolutional layers. And these blocks learn different representations. So it will learn to find edges or different colors. And so each one, as you go through layers, it'll have a higher order representations or more abstract representations as you go through the layers. And so depending on which representations are triggered, you'll get a output or an estimate. So this is what the ResUnet CMB is. And so just like this example where we have to input something, our input here, or what we're going to be making our estimates from, are observations of the Q and U polarization of the CMB. And so the simulation pipeline to create these observations are, we take a theory spectra and we make a Gaussian realization of the primordial Q, just has no effects on it. And then we modulate it by tau, which we also produce with theory spectra. Then we lens the modulated Q map. We also add beam and we add noise. And then finally, we add a taper for a 1.5 degree taper to reduce edge effects when we actually take FFTs and stuff like that. So this is the simulation pipeline. So we'll train the network on these images, as well as we'll make our predictions of tau from these images. So essentially we'll feed in this map to the network and we'll try and recreate this tau map and this kappa map. And so this is the ResUnet CMB network. The convolution block is defined here. So the network is made up of multiple convolution blocks with, multiple different layers. But the basic idea is the same as the handwriting digit, where we input the Q and U observed maps, and it goes through the network. It learns different abstract representations, what to look for, how to reconstruct kappa, tau, and E. And so we train it first by inputting Q observed, U observed, and then we give it the true values for kappa, tau, and E, what we actually want it to learn. Then once it's fully trained, we can just input any random Q observed, U observed, and it'll make predictions on what it thinks it should look like. And so here are the results from a fully trained model. So we input, as I said before, the Q and U maps, and the goal is to create this, get these maps back. So the predicted for noiseless, which is no instrument noise. As you can see, for the tau, we are able to get a lot of the high level structure, but we still miss quite a bit. But the high level structure is there, and when we increase the noise, the reconstruction gets noticeably worse, but we still are able to reconstruct some high level features. For the other two, the residuals are quite good, the reconstructions are quite good, which is to be expected since these, since especially kappa is magnitudes greater than the signal from tau. But while this shows promise, the real goal is, or the real eye opener is looking at the reconstruction noise curves. And so for These are the reconstruction noise. We did it for multiple noise lists: 0.2 microarc minute, 1 microarc minute, 2 microarc minute. As mentioned before, if you do a naive application of the tau quadratic estimator, it will be biased by lensing, which is what's shown in this purple and green, where purple is negative and green is positive values. And so this is the lensing bias in the quadratic estimator. And so the big thing to note is the ResiNet CMB, the reconstruction noise, is below the dashed line, which is the quadratic estimator noise using lensed CMB only. So no delensing was done at all. And so we already do better than that for a good portion, the lowest noise, and then for a moderate important L range for the higher noise levels. The very impressive thing is that our reconstruction is actually able to mimic or it follows closely to the reconstruction noise of the iteratively delensed and descreened CMB quadratic estimator. So the spectra were delensed and descreened and using normal methods. And we find that the ResiNet CMB actually approaches that estimate, or approaches the reconstruction noise of that method without us actually having to implement it or train it. So it just learns to optimally delens and descreen in the same way that you would program to do. So it efficiently predicts both tau and lensing while doing it in a very optimal way. And so this is just another way to see that the ResiNet CMB is not exactly affected by the bias in the low L or the large scales, where the orange curve is the ResiNet CMB and the blue curve is the quadratic estimator. Quadratic estimator, these are averaged over, or these power spectra are averaged over multiple realizations. So the noise is really beat down, so we really just get the spectrum. And so you can see the quadratic estimator. 1 minute, please. Okay, yeah, I think this is fine. The quadratic estimator follows the bias closely, but at the low range for especially the low noises, the ResiNet CMB doesn't experience the same bias. And so, in summary, ResiNet CMB outperforms quadratic estimator at low noise. It reduces lensing bias experienced by the tau estimator. It reconstructs both very optimally, and the network itself can be easily modified. If you just want to reconstruct lensing, you can just remove the 2 other outputs. If you just want to reconstruct tau, you can remove the other output. So it's easily modified. Where do we go from here? We can add realism and complexity to the simulation, such as foregrounds, so that it can eventually be used for upcoming observations that can just be fed in. Thank you.
Thank you very much. Let's save time for one question. Any? I just got one. Did you try different size of images and see how it reacts, and if the UNet is more able to get better results as you have a bigger part of the sky, or
right?
Is it limited by the UNet itself? Or?
Right. So the images we used were 128 by 128, 5 degree by 5 degree images of the sky. And so if we increase the size, we'll find better results at the large L, but the low L is still causing some issues. Okay. Or we'll find better results at low L, but the high L will still cause some issues. But the sizes of the images or the resolution definitely will be looked into further as well to find the optimal one.
Okay. Thank you very much. I think again we can continue the questions on the Slack. So we have now a break. Okay, we are a bit late compared to the schedule, but let's say that we start at okay 6 p.m. for us, whatever p.m. it is for you, or a.m. it is for you. Let's say in 8 minutes, if it's okay. And the next talk is Gabriella. So see you in a few minutes after some coffee or at least fresh air. Hello, Gabriela.
Hi.
Hello.
I think you can start sharing your screen.
Okay. Okay, can you see everything?
Yep.
Okay, should I start?
Yeah. So we. What time is it? 1 minute still.
Okay.
So it's 15 minutes, and if you can allow some time for questions. Okay, I don't see anymore if everybody is back, but okay, let's start the second session this afternoon with Gabriela Satopolito on KZ tomography with line intensity mapping. So please, you can start.
Okay, thank you to the organizers for inviting me. I'm Gabby, I'm a PhD student at Johns Hopkins, and I'm going to talk about KC tomography with line intensity mapping and the results of this paper that we put out earlier this year. So as you know, CMB photons produced at the surface of less scattering have to travel across the whole universe before getting to us, where we get to detect them. And as they do that, they can interact with intervening matter, which imparts secondary CMB anisotropies on the CMB. And in particular, if these CMB photons scatter off electrons that are bound in moving structures, this can impart temperature fluctuations that are proportional to the distribution of electrons and the velocity, the line of sight velocity that these structures are moving with, which is known as the KSE effect. So the KSE effect will receive contributions from essentially everywhere that free electrons are available, and so mainly from the epoch of reionization and from ionized gas in galaxies and clusters in the post-reionization universe. And so at these very small scales where this effect becomes one of the dominant effects on the CMB, this is really tracing the large scale structure of the universe. And so it has been and can be profitable to consider cross correlations between large scale structure and the CMB. So this has been done. There are a variety of detections of the KSE effect by considering these cross correlations. More recently, with ACT and BOSS. Apologies for the incomplete list. But in terms of this little diagram of the evolution of the universe that we have, the regions that we can directly probe look more like this, right? We can probe directly with galaxy surveys only up to a certain redshift, and these measurements become very, very challenging as we try to push to higher and higher redshifts. The brightness of galaxies will decrease, and these number counts will become smaller and smaller, even if we consider very like next generation galaxy surveys. And so a technique that has gained a lot of traction as a way to probe this kind of intermediate redshift range is line intensity mapping. So line intensity mapping measures the intensity fluctuations in atomic or molecular line emissions. And it captures the integrated emission from all sources, whether they can be individually resolved or not. And so they have the potential to trace the matter distribution over a very wide redshift range, potentially from today up to the dark ages. And so typically what we wanted to do in this project was to fold in line intensity mapping into this picture of CMB across large scale structure. And so in the post-reionization universe. So I just wanted to stress that here, that the signal that we consider in this work is in the post-reionization universe, but the techniques that we use are very general and can easily be applied to studies of reionization. And so for reionization studies, typically you want to consider, for example, the 21 centimeter line. But there are, of course, a variety of different lines that trace, different atomic and molecular lines that trace different phases of the interstellar and the intergalactic medium over a very large chunk of cosmic history. And so in this work, we focus on the C2 line, which is a very good tracer of star formation. And so it kind of peaks in this intermediate range, redshift like 2 to 3. And so we focus on this line, and we want to essentially be able to say something about the detectability of this KSE signal with LIM as a tracer of large-scale structure, and to understand better what we can say about relevant cosmological parameters. And so the way that we approach this is using this KSE bispectrum framework. So in this paper by Kendrick Smith and others, they show that a lot of these different statistical measurements of the KSE effect are, there's a unifying approach, this 3-point function between 1 power of the CMB temperature and 2 powers of a tracer of large-scale structure captures the signal in a lot of these different statistical approaches. And so this is how we model our KSE across large-scale structure signal. And of particular interest is the fact that this approach also includes this radial velocity reconstruction. And so you can basically think of this as small scale temperature and matter fluctuations evolving on this like background mode of the large scale velocity fields. And so you can essentially recover the large scale velocity mode by averaging over these small scale modes in a very analogous way as like lensing reconstruction works, where you're averaging over small scale temperature perturbations to recover the lensing potential, the lensing potential. And so this is the approach that we adopt in this work. We look at the detectability of this signal with different combination of future experiments. We separate this roughly in like 2 time scales, one for like nearish future experiments and one for like more distant future experiments. And so for this new near future set of experiments, we consider the epoch of reionization spectrometer in CCAT prime and Simon's observatory. And unfortunately, we do not find that a significant detection is possible with this like first light instrument design. But we did want to ask, like, how much would you have to like beef up this kind of current technology to be able to get a detection? And we have this essentially, we show that with you know, longer observation times, with like the full survey area, et cetera, we can, in fact, it is in fact possible to get a KSE detection at these very high redshifts. And so next we consider these next generation experiments with ATLAS and CMB+EOR, and we show that over this very wide redshift range that we can get a very, very significant detection of the KSE with C2 intensity mapping as a tracer of large scale structure. And I just wanted to highlight that in the paper, we go through this like more detailed investigation of, you know, what would you need from a line intensity mapping experiment to be able to do this? What scales in particular from that you can recover in the velocity field, depending on your different instrument configurations. But I omitted that in this talk, but I encourage you to look at that there if you're interested in that. And so essentially, you know, line intensity mapping gives us this opportunity to probe these very difficult to access volumes of the universe. And so we're pushing to higher redshifts, which gives us just more volume in the universe to probe. We can also reconstruct the large scale velocity fields. And if you recall from the continuity equation, the scales as inverse K. And so you're really getting back for very large scales, small K, this recovery gets better and better. And so you're probing these very large density modes. And with these 2 different tracers of large scale structure, with your limb intensity fluctuations and with this reconstructed velocity that you get from this cross correlation between limb and the CMB, you can do this like multi-tracer approach and achieve cosmic variance cancellation. So all of these things are pointing at the fact that we're doing better for the largest scales in the universe. And so this motivates us to look at phenomena that would impact, physical phenomena that would impact these largest scales in the universe. So as a kind of case study of what we can do with like all of this technology, we look at constraining different theories of inflation. So we consider these two like general signatures of inflation, primordial non-Gaussianity and compensated isocurvature perturbations that induce this like scale-dependent bias, which changes clustering at the very largest scales in the universe. So yeah, we parameterize primordial non-Gaussianity through FNL, and for compensated isocurvature perturbations, so isocurvature perturbations are these relative fluctuations between like different components, between different species in the universe. And so this is a general prediction in like multi-field inflation. And so we consider in particular fluctuations between baryons and dark matter that leave the total matter unchanged. So the total matter fluctuation is adiabatic, and we parameterize this as through this parameter A, which is essentially this relation between the isocurvature and the adiabatic modes. And so these two components will, again, induce this scale-dependent bias. And they do that and they affect the clustering at any given redshift in identical ways. But by looking at this broader range of redshifts, we can separate these two contributions because they evolve differently in redshift. So in this picture, you can see here, this is the results of a Fisher forecast. If we compare the left panel, which is with only a power spectrum measurement with a line intensity mapping experiment, with the panel on the right, which includes this like clustering measurement in the inline intensity mapping with this reconstruction of the velocity with the CMB. The contours are about 3 times smaller, so we get like about a 3-time improvement in these constraints. And if we compare the contours for each that correspond to different redshift ranges, you can see this this degeneracy being broken in these two parameters. As you add these contributions together, they have different degeneracies, and so we get to separate these two contributions to inflation. So yeah, these are the main points that we found. That intensity mapping in the KSC can be a powerful probe to the early universe. We have access to more volume. We can probe large scale modes, and we see about a 3-time improvement by including this velocity reconstruction from the KSC with our line intensity mapping experiments. And this can really help us, exploit all of the information that will be made available with this these new sets of experiments, and we can distinguish these different contributions from inflation in this way. Thank you.
Thank you very much. Any questions? I'm checking all the. So there's a question from Emmanuel. Thank you for the great talk. Does this KZ detection require measuring the low K parallel or K parallel equals 0 mode for the anticity map?
Sorry. The K parallel mode, was that the question?
Yeah. Does it need to be?
Yeah. Yes. It is a part of the signal.
And the relative question is this possible in the presence of continuum foregrounds in the intensity map?
Yeah, so that is a very good question. It's definitely a challenge that these kinds of measurements face. I would say that, for example, I'd say that C2, for example, and like CO, these other lines that aren't 21 centimeter do suffer a lot less from these issues. So it's not as dramatic as you're probably thinking about with 21 centimeter measurements, but it's certainly a problem that needs to be addressed.
And then another question, how do you forecast FNL constraints compared to the Planck one?
So for like comparing the different, so for the,
sorry, go ahead.
Yeah, so for this plot here, we are like varying these two measurements simultaneously, along with like all the other cosmological parameters and like bias parameters that we marginalized over. If we do limit, for example, if we fix ACAP, these constraints are shown in our paper, and you do get like a much better constraint than shown in this plot. And so for these like very futuristic experiments, we do get to like order unity for sigma FNL.
Thank you. I just have a quick question. When you made the forecast with CCAT and SO,
Yeah.
you kind of fixed the redshift to 3.7.
We took the lowest redshift bin
Okay.
for this, yeah, just
And
to
that just-
include like the to not include the reionization signal essentially.
Okay, but you could have like 2 bins at 3.7 and 4 or something, or is it?
Yeah, we use the binning that CCAT prime intends to use,
Okay.
and we only choose the lowest bin
Okay,
for that reason.
thank you. Thank you very much.
Thank you.
We can move forward to the next talk by Adeligos about better accounting for reionization in CMB data analysis, the KZ effect.
Yes, thank you, Marion. So, hi everyone. So I'd like to take the opportunity of this conference to introduce to you the work we did, so with Marion partly, and also Stéphane Illich, Dominique Aubert, Mathieu Langer, et Laura Salvati, on the KZ power spectrum. And that's actually the work that made us think about what was available today to constrain reionization with CMB data. And doing this state-of-the-art, this benchmark, we thought about organizing this conference. So I hope it'll be useful not only for us, but also for everyone. So in our work, we tried to find a way to analytically compute the KZ from a few parameters that are related to the epoch of reionization, and not only the global history, but also its morphology. So start quickly with the KZ effect. We've had a few talks about it already, but just in what we're interested in today, what we're interested in is the power spectrum. So you're going to add power in the temperature CMB power spectrum with the KZ effect. And there are 2 contributions you can have from this. So the late time KZ, which is what Gabriela was talking about, and the patchy KZ that comes from the scattering of CMB photons of ionized bubbles along the line of sight during reionization. And that's what we're interested in today. So these 2 components have different shapes in terms of power spectra. And interestingly, the patchy KZ is expected to reach its maximum amplitude, maximum power, at an angular multiple that roughly corresponds to the typical size of ionized bubbles during reionization. So the way we use CMB data, mostly at the moment to constrain the KZ power spectrum, is that we choose templates, such as the 2 ones I show on the left panel, and then we fit their amplitude at a multiple of 3000 to data, along with other foregrounds naturally. So with this, you can then interpret the constraint you get on the amplitude at L equals 3000 in terms of reionization scenarios, because you have scalings, for example, that give you the midpoint of reionization, so the redshift where 50% of the IGM is ionized, and the duration of reionization in terms of this parameter here. So that's, for example, what's been done most recently by the SPT team, which find combining Planck and SPT data a constraint on the amplitude of the patchy KZ, and they deduce a constraint on the duration of reionization from this. However, there's a few issues with this approach, and we tried to do something that is more precise. Here are the issues. The first one is that we use templates for the KZ power, even though we know that not only the amplitude, but also the shape of the KZ spectrum depends on the reionization scenario. Then the scalings that are used to translate the KZ amplitude into EOR parameters are largely dependent on the simulations they were calibrated on. And finally, you actually use a different reionization history when you analyze large-scale data and small-scale CMB. So you have a bunch of inconsistent hypotheses, and so that's what motivated us to try and develop this semi-analytic derivation of the KZ power that would bring everything back together. So as an additional motivation, I see here, I show here the example KZ power spectra you get for 3 simulations. So these are 3 simulations of reionization. They correspond to different prescriptions for the escape fraction of ionizing photons from the host galaxy. In one case, it's constant, equal to 20%, which is roughly the fiducial value. In one case, it's proportional to the fractions of baryons ejected from the galaxy. And in the final case, it's proportional to the star formation rate of the galaxy, and so roughly of the mass of the host halo. But what we're interested in here is that these 3 different models result in different morphologies of reionization, with at 30% ionization, the SFR simulation, for example, having the largest bubbles on average. So if you compute the KZ power from these 3 simulations using the templates and the scalings, you will obtain the dashed line here. So they're mostly all similar. Although if you use the method I'm about to describe, then you get the 3 solid lines where you see you have not only a difference in power, in amplitude, but also in shape. And in particular, here you can notice that the simulation with the largest bubbles on average, the blue one, is also the one that has the maximum amplitude at the larger angular scale, so the smaller angular multiple. So how can we do this? Well, we went back to the basic equation giving you the CLs of the KZ power and looked at the different elements. So you have a few elements that are gonna just characterize the amplitude of your signal. So the Thomson optical depth here that we've talked about already, the mean density of electrons as a function of redshift, and naturally the limits of the integral, because we're looking at the patchy KZ power spectrum. So we're integrating over the duration of reionization, and naturally, if it lasts for longer, then you have more power. Then you have this term here, which is a power spectrum, and that is going to completely define the shape of your spectrum. And so that's what we chose to focus on. And in particular, we found an easy way to express it in terms of the power spectrum of the overdensity of free electrons. So we looked at how this power spectrum evolves in time in a highly resolved radiative hydrodynamic simulation. And so you see that at the beginning, the structure is very simple, just flat, and then it decreases. And as time goes by, electrons start to follow more and more the matter distribution. And so you end up with something that is purely a biased matter power spectrum. So if we focus on the early time power spectrum of electron density, we can easily parameterize it in terms of 2 parameters, alpha naught and kappa, and the global history of reionization. So the first one, alpha naught, is just the amplitude of the constant amplitude of the power spectrum on large scales. And because it's the amplitude of the power spectrum, then it's going to be related to the variance of your field. And naturally, it's going to be related to the morphology of reionization, because you can imagine that if you have only a few but very large ionized bubbles in your field, then your variance is going to be much higher than if you have a lot of tiny ionizing sources that are not very efficient ionizing, and so a lot of very small ionized regions. The other parameter is the parameter kappa, which is the drop-off frequency. So it's the frequency over which your power decreases as k to the -3. So you can imagine as well that if there's no power on scale smaller than kappa, then it means that basically you do not have ionized regions that are smaller than this. At least that's the intuition you can have. So from this easy parameterization, we get a fit-in formula with an early time part, a late time part. We fit it to different types of simulations. We get posteriors on alpha naught and kappa. We know the reionization history. And so we can derive the KZ power spectrum completely analytically. So we first did that on the EMMA simulations that we started working on, that were simulated in Strasbourg. And then we also chose to analyze 2 different types of simulations. So the SAGE one I mentioned before, and also 3 different runs of the 21 centimeter fast simulations, which are quick and easy to run semi-numerical simulations of reionization. The idea was to check if our parameterization was specific to the first simulation we looked at, or if it could be actually used on many different types of simulation. It was general enough. So here are the results. First, let's look at the left column, so the MR simulations that we used first to do this. And so we have two models for these two simulations, one where the star formation has been doubled compared to the first one, and this results in reionization happening earlier, naturally, than with a lower star formation. But interestingly, the effect on the KZ power spectrum is not only to increase the amplitude, as we would expect, because you integrate over higher redshifts, but also to change the shape. So that shows you that just looking at global history is not enough to have the full information. Then we have the 3 SAGE simulations. So if you remember from the pictures I showed at the beginning, they had very different morphologies. And here they have pretty similar reionization histories. However, their resulting KZ spectra are clearly different. And we noticed that, as I mentioned before, the SFR simulation, which has the largest bubbles on average, also peaks at the smallest angular multiple and has the largest power. Then finally, we have the 321 centimeter fast simulations for 3 different values of the turnover mass. That is the minimal mass under which there's an exponential suppression of star formation. So basically, for the largest value, so 10 to the 10 solar masses, you need very, very massive halos to have star formation and to have ionization. So you delay your reionization a lot compared to the 2 other simulations. And so the effect is the following. For low values of this parameter, you have smaller ionized regions because they're less efficient at ionizing, and you reionize earlier so that you have a higher amplitude, and you peak at higher Ls. And reciprocally, for the 10 to the 10 solar masses, you peak at smaller angular multiples. So then our question was, so we have parameters that we know now can describe pretty well the KZ power from a simulation, but how can they relate? How can them relate them to physics and to the physics and morphology of reionization? So I mentioned first the kappa parameter here, so the frequency where the power spectrum decreases. And we find that for all the simulations we're looking at, a smaller kappa always means larger bubbles. And we can also directly relate it to the angular multiple where your KZ power is maximum, and that is independent of the reionization history, the reionization model, and, for example, alpha naught in particular. So it means that if you measure the KZ power, then you can directly derive kappa and get an estimate of the typical size of ionized bubbles. The second parameter is alpha naught. So as I mentioned before, because it's the amplitude of the power spectrum, you expect it to be correlated to the amplitude of your power spectrum, but it's a bit more complicated than that because it's also correlated to the size of your bubbles. And so in general, you can see it's correlated with the multiple where your power is maximum, but also to the amplitude at d to the at L equal 3000, sorry. And so it's correlated to a bunch of other information related to reionization, and you will need to cross-correlate with other data, such as 21 centimeter intensity mapping, to break the degeneracy. So as a conclusion, you probably all know that the high-quality CMB data is still coming, maybe not just coming. And so to make the most out of it, we improved the way reionization is modeled in CMB data analysis, which also include cosmology and reionization in the KZ power extraction to enclose information about reionization history and morphology. So we have 2 parameters that we understand really well and that will allow us in a second time to cross-correlate with other data sets. So for example, if we measure alpha naught or the typical size of bubbles from CM 21 centimeter intensity mapping. So that's the 2 different paths we want to follow after this paper. So first use it to try to detect the amplitude and shape of the KZ in data. So we're currently implementing all this formalism within Cosmo MC to use on SPT data, also doing forecasts to see what we could get with future experiments. And we're also trying to include this in 21 centimeter data analysis framework. So for example, 21 CMMC, which is MCC sampler of 21 centimeter fast simulations. Yeah, so that's all I had to say today. I'm happy to take questions if you have any. Thank you for your attention.
Thank you. We have 1 minute for question, if any. Just have to check again all the things. Oops, sorry. Okay. Well, I'm not well placed to ask questions. I won't ask you any. Okay. Anyway, the chat is always open to ask questions later on, so don't hesitate. Thank you, Adedi. Hello, Abby.
Hi.
How are you?
I'm good. Thanks.
So it's now your turn for this last talk of this small session in the middle. Improve KZ measurement from the CMB data and constraints on reionization. So you can share your screen.
Perfect. Thanks. Guess
we have your desktop. Yeah. Okay. Great.
Okay. Let me just get this out of the way. Okay. So the presentation is visible, I guess, with the mouse moving. All right. So I'm Abhishek Maniar. I'm a postdoc at the Center for Cosmology and Particle Physics of the New York University. And today I'll be talking about the how we plan to improve the KSZ measurements from the CMB power spectrum data and potential constraints on the reionization. So this work has been carried out in collaboration with Matthew Twistrom and Xavier Garrido in Paris and Irene Lagache in Marseille. So yeah, before getting to the actual talk, I would just like to point out something that probably most of you already know, that the COVID situation in India is kind of really bad right now. It's very horrendous. So if you have any Indian colleagues, I would urge you to reach out to them or help in any way if you can. But okay, let's get that out of the way. And now we can jump to the technical aspect. Okay, so the motivation for all of us trying to understand reionization, some of the pressing questions are, when did the reionization happen and how long did it last? And there are several other questions as highlighted by Subodip and others today. And so ultimately we would like to have a plot like this where we could constrain both the duration as well as the actual time of the reionization, beginning and the ending together. So that would be the ultimate plot to have, where we could constrain both the quantities really well. And the tools which we are normally used for answering these questions are quasars and their Gunn-Peterson troughs, or 21 centimeter line emissions, and CMB anisotropies, which have helped us to understand the reionization relatively okay till now. So this is the main motivation. But then why the tool which we will be using here, it falls under the category of the CMB anisotropies, mainly the kinematics and Nasual-Dage effect. And so why would I be talking about KSZ effect has been explained by the speakers beforehand, so I will not spend a lot of time on this, but just tell you that the Nasual-Dage effect is, the thermal part is basically when you just have this inverse Compton scattering of the CMB photons from the highly energetic electrons in the galaxy clusters. And then when the hot plasma has this bulk motion, apart from the TSZ, you also have a Doppler boosting which Doppler boosting in that radiation, which is called the kinematics and Nasual-Dage effect. And the feature of this KSZ spectrum is it has a black body shape very similar to the primary CMB. So that's the KSZ effect. And why do we talk about KSZ in the context of reionization? As I said, this has been explained very well by the previous speakers, but nonetheless, KSZ, as we have seen, has a patchy and homogeneous component. The patchy component has its origin in the when the reionization is actually taking place, and the homogeneous component happens when the reionization finishes till now. So that's what gives us the total KSZ power spectrum. And so that this just tells us that if we are able to measure the total KSZ power spectrum really well, we can potentially constrain the patchy component of the reionization, and that will give us an idea of how long the reionization lasted, as well as when did it actually happen. So that is the motivation in measuring the KSZ power spectrum from the CMB data. Now, okay, this seems straightforward, but is it really? So this is how this is the signal we are trying to measure, namely the dotted dashed blue line here in every panel. That is the KSZ power spectrum. And this is the red is the original CMB. The other lines, blue, orange, green, they represent different foregrounds, namely the thermal Sunyaev-Zelldovich effect, then the CIB, cosmic infrared background, then you also have galactic cirrus or radio short noise. And on top of that, you also have the correlations between different foregrounds. For example, the TSZ and CIB are expected to be correlated because they are both tracing the large scale structure to some extent. So as you can see, first of all, our signal is really small, the signal we are trying to measure. And on top of that, it's dominated to some extent by the primary CMB, but also the foregrounds to a large extent. So this is really challenging. And on top of that, as I mentioned, there are correlations. So for example, the CIB and TSZ are expected to be correlated. And then in turn, their measurement is correlated with the measurement of the TSZ or the KSZ, which we measure in the CMB data. And similarly, the measurement of the TSZ itself is as a result correlated with the measurement of the KSZ. So this plot I'm showing just to give you an idea that as the data quality keeps on getting better and better with the sensitive experiments like SO and S4 coming up, I think it's better. We all need to be careful while doing such kinds of analysis. Mainly, we need to be careful using precise models for the foregrounds, and that's why and as a result get better measurements for the reliable measurements for the KSZ power spectrum. Now, first that has been made clear what has been the current approach and what have been the limitations for the current approach. So what is normally done right now is we either use power law or best fit templates for these foregrounds, for namely the CIB, TSZ, and their correlation. So when you use something like a best fit template for these foregrounds, what you do is basically you assume a shape, and you fit for an amplitude across all the same amplitude across all the frequency channels. So this is not really appropriate because, first of all, this assumes that for example, for the CIB, it assumes that the different frequency channels are perfectly correlated, which we know is not the case. And then also it assumes that there is no scale dependence. There is no scale dependence in the shape of these templates, which also Adeli also in her last talk mentioned that KSZ, for example, can have these effects which can show up potentially. So this approach probably is not the best one. And also sometimes when these templates have been considered in the past, the CIB and TSZ templates, they are not consistent with the templates used in the CIB TSZ correlation. So there is this inconsistency as well. So what we would like to do is we would like to have a physically motivated but simple model for the cosmic infrared background and the thermal Sunyaev-Zelldovich effect. Based on that, we would like to have a consistent halo model this time for their correlation, CIB TSZ correlation. And then we would like to we would like to also consider the cosmology dependence of these foregrounds in our likelihood at every step of the likelihood. And also we would like to take advantage of all the data available to us, high frequency and low frequency data, namely Planck, SPT, Herschel, and Planck CIB data. So that's what we would like to do. So the first step, as I mentioned, is we would like to have a new Hello model of the CIB. Now, why a new Hello model? Because there are previous Hello models in the which have been developed, but we don't use them because, first of all, they rely on these luminosity to Hello mass relations, which don't start from a very physically motivated perspective, and they also have a really high number of parameters. And especially in a study like this, where you have a lot of parameters already coming from the primary CMB analysis and other foregrounds, you would ideally prefer to have less number of parameters. And also the results from the previous Hello models of the CIB, they are not consistent with the results from either the linear models or the data. For example, when you measure the star formation history of the universe, the results you get are not consistent with the results you obtain. The SFRD measurements from the external galaxy surveys are not consistent with the results from the previous Hello models. So that's why we developed a new Hello model for the CIB, which is very simplistic. In short, what we do is we start from a very naive but physically motivated argument that we start from the accretion on the dark matter halos. So the dark matter halos grow over time through accretion, and then some of this accreted matter is the baryonic matter, and this baryonic, we assume that some of this baryonic matter gets converted into stars with some efficiency. And once we have some form of that efficiency, we can convert that efficiency to the star formation rate corresponding to a given Hello mass at a given redshift. So, and once you have that star formation rate, what you can do is you can convert that into the potential CIB power spectra. So this is our basic simple model. We have just 4 parameters, and with those 4 parameters, we were able to fit both the Planck and Herschel data, which we show here, the power spectrum measurements for the Planck and Herschel data. And at the same time, the big improvement is we were consistent with the SFRD measurements coming from the linear model, which we show here. This is from the Hello model, and this is dashed lines in black are from the linear model. So this is a big improvement over the previous Hello models. So, and considering that it had just 4 parameters, this is fantastic. Then, as I said, we also have we use the TSZ Hello model, which is normally used in practice, and we consider both the 1 Hello term and the 2 Hello term. 2 Hello term is normally neglected sometimes because it's really small, but we do consider it here in our analysis. And the only parameter we have in this case is the mass bias parameter for the TSZ. So we have 4 parameter of the CIB and 1 parameter of the TSZ. And using these 2 Hello models, we make a consistent CIB TSZ power spectrum Hello model, which does not require any extra parameter. So just for 4 CIB and 1 TSZ parameter. And here I'm showing the CIB TSZ power spectrum contribution coming from different redshift beams for 2 different pairs of frequency, 2 frequency pair channels from Planck. There are many interesting things happening here. I would like to, at some point, I would like to explain many things happening in this plot, but in the interest of time, we'll skip them. And I will just highlight that if you see the 2 Hello term here is given by dot dash line. So if you see for every redshift bin in both these panels, that the 2 Hello term is non-negligible when you compare it with the 1 Hello term, which is given by the dashed line. So in this analysis, we should not neglect the 2 Hello term, and we should consider it. And there, as I said before, there are some other interesting things happening from the astrophysical point of view, but let's skip them for now in interest of time. All right, so our approach and where are we right now? So we have developed a physically motivated Hello model and simplistic model for the CIB and TSZ, and we have constructed a consistent Hello model for CIB TSZ correlation. We are using the helipop likelihood to deal with the Planck data, we have combined the Planck and SPT data for the CMB data analysis, CMB power spectrum analysis, and we are using the Spire and high frequency instrument data from the Planck just for the CIB data. And we also have measurements from the external galaxy surveys for the SFRD to include that in our likelihood. Now, for integrating all of this, we are using Cobaya. What we have done is we have replaced the old templates for foregrounds with these Hello models. So no more templates, only the Hello models. And then we are explicitly considering the cosmology dependence of all the foregrounds at every step of the MCMC. And then currently we are in the process of integrating the SPT likelihood, basically, namely the removing all these templates from SPT likelihood and putting in our Hello model. And once that is done, our next steps are to perform a combined likelihood MCMC analysis with all this data, hopefully get new constraints on the KSD power spectrum. Not sure how improved they would be, but we'll see. And then potentially constrain the reionization, like see if we have some new results based on that. So that's it. Thanks.
Thank you very much. Any questions for Abby? Sorry, I have to stop the clock before it's ringing. There's one question on Slack. So the question is, how do you compute the one Halo term? Doesn't your Halo model only tell you the properties of the central galaxy from the accretion rate onto the Halo and no sub-Halo?
Right. So here what we assume is we have one central galaxy, and in a given Halo we have one central galaxy, and we have satellite galaxies which are distributed according to the NFW profile. And we have different procedures for calculating the star formation rate for a central galaxy and the satellite galaxy. So we do consider both the contributions. And as far as the one Halo and two Halo terms are considered, so as I said, we have one central galaxy and several satellite galaxies. So that is also one of the terms included in our likelihood when we calculate the one Halo term, namely the interaction between the satellite and central galaxies and interaction between satellite galaxies within a given Halo themselves. So that is considered. We don't neglect it. And it turns out it is actually a very important term on small scales, as you can see here. Around when you go to L of 2000, 3000, multiples of L 2000, 3000, the one Halo term does actually dominate over the two Halo and short noise to some extent. So we do consider it.
Okay. Thank you.
Yeah.
Thanks for the three speakers of this session.
Right.
Let's have a 15-minute break until whatever o'clock it is in 13 minutes. And we will resume with the three last talks of the day. Good break. Okay. Hello, Nyani.
Hi, Mary.
Can you start sharing your screen?
Sure.
So we're starting the last session of 3 talks. First one with Nyani Shen, simulating patchy KZ with semi-numerical code Amber. And again, you have 15 minutes. And people, please ask question on the Q&A Zoom or in the Slack. And I will pass the question at the end of the talk. When you want.
Okay. Thanks. It's a great pleasure to be here and talk about our work. Hi, everyone. I'm Nian from Carnegie Mellon University. I'm currently a third-year PhD student advised by HeTrack. And today I would like to tell you about our work on simulating and emulating the patchy KZ effect with a new semi-numerical code for reionization, Amber. I'm sure you've already heard about this plenty of times, but the patchy KZ effect is due to the Bach motion of free electrons scattering off of CMB photons. And the KZ signal can be calculated by integrating the free electron momentum along the line of sight. And why do we care about KZ? Why is it important? So first of all, it provides constraints on the redshift and duration of reionization. And furthermore, we would need to understand the KZ effect in order to be able to separate from other observables like the homogeneous KZ and CMB lensing. So for this work, we would like to address 3 main problems about modeling and simulating the KZ effect. So firstly, we would like to be able to simulate patchy KZ in large volumes in order to capture the large scale velocity modes. And secondly, we will also want to simulate the KZ fast in order to be able to carry out parameter space studies. And finally, because our main goal here is to constrain the reionization history, we would like to allow for a flexible and direct control over the reionization history by making it a direct input into our simulations. So with these goals in mind, let me introduce the Amber code, which is a semi-numerical code for simulating the EOR based on abundance matching. So since this is not a method talk about a simulation, I'm going to skip all the details here and just bring your attention to 4 parameters that we would like to study for this work. So the first one is the photon mean free path, which controls how far the photon can travel in the IGM, and inter controls the morphology of ionized regions in the simulation. And the next set of parameters are the reionization history parameters, which are the midpoint, redshift, the duration, and the asymmetry of reionization. So let me explain more here. So this is a plot of the mass-weighted ionization fraction. And Z mid here means the redshift at which the universe is half ionized by mass. The duration is the difference in redshift between the beginning and the end of reionization. And the asymmetry parameter captures the relative duration of the early part and the later part of reionization. So with these 3 parameters altogether and the Weibull function, we're able to parameterize the reionization history as a direct input into the simulation. And then with this reionization history, we will abundance match against the radiation field to construct the reionization redshift field. And so combining all of these fields, we're able to produce observables like the tau and KSZ maps and power spectrum from the simulation. So now we have an idea for a semi-numerical code. How do we know that it's functioning correctly? Well, so we calibrate our semi-numerical code Amber against a suite of full radiative transfer plus hydro simulations, the scorch simulations. So first in the top panel, I show a comparison between the reionization history from the scorch and the Amber sims. So you can see that with the parameterization and our 3 reionization history parameters, we're able to recover the different reionization history from the scored simulations to within percent. Moreover, when we actually match all of these parameters and calibrate the mean free path parameter, we can simulate the reionization redshift field with amber that looks very close to the scored simulation. And we go further by looking at the actual CMB observable maps. So here on the top panel, I show the distribution of the KZ signal and the angular power spectrum under the flat sky approximation. And you can see that in both cases, the amber result agree very well with the scored simulation results. And on the bottom panel, I show a visualization of a 2D flat map from the two simulations. And they also look very close to each other. And so now we see that the amber code actually reproduced the scorched result really well. We begin to simulate amber in very large volumes. So here I show a full sky map from a simulation with amber. So this is a 2 gigaparsec box with 2048 cubed grid cells. And this simulation can actually be done in a few hours on a single compute node, so it's pretty fast. And in the bottom panel, I show the patches of these maps, but varying the duration of reionization. So in the left panel, we have a reionization scenario with a short duration, and you can see that the map is relatively smooth because with a short duration, we can see less ionized bubbles along the line of sight. And when you go to the right panel, as you increase the duration of reionization, you begin to see more and more of these small scale features. And this is because the reionization extends further back in time when the universe is denser. So in the previous slides, I only vary one parameter, which is the duration. So next, we would like to see how the KSZ angular power spectra actually depends on all 4 parameters of reionization. So the top 2 panels are relatively well-known results, namely that when you have an earlier reionization, you will observe a higher overall amplitude of the KSZ angular power spectrum. And this is because the electron number density is higher at high redshifts. And the second panel show that when you have an extended reionization scenario, you will also observe a higher overall amplitude. And this time it's because when you have an extended reionization, you will see a stacked and more ionized bubbles along your line of sight, which boosts this overall amplitude of the power spectrum. And on the bottom panel, I show the results that are less obvious. So first, we vary the asymmetry parameter in a wide range and see whether the power spectrum is affected by the asymmetry of reionization. And you see that what's important for the asymmetry is the overall slope of, or the shape of the angular power spectrum instead of the amplitude at a particular point. And note that here, for example, if you pick the L equals 3000 point and only measure this single point, you will actually see no variation when you vary the asymmetry of reionization. But if you're able to observe more points along this line, you can actually capture the dependence on asymmetry pretty well. And finally, we vary the photon mean free path in the simulation. And remember that if you have a small mean free path, you will result in a smaller ionized bubbles. And if you have a large mean free path, you will see a larger ionized bubbles in the simulation. So because the size of the ionized bubbles is directly related to the peak of the angular power spectra, when you increase the mean free path parameter from 1 to 5, you see a shift of the peak of the angular power spectrum from L equals 2000 down to L equals 1000. So next, we look at the scaling relation of the KSZ power spectrum magnitude at L equals 3000 with 2 parameters. The one is delta Z and one is at the midpoint of reionization. And in both cases, we see almost linear scaling with these two parameters according to our simulation. So far I talked about the results from the semi-numerical code, which is great and it's fast. However, we want to ask the question, can we go even faster? Because with like hours of simulation, it's not possible to do a full parameter space study or likelihood analysis. So we have this idea of building an emulator from the simulation data, which is able to produce the full KZ spectra in seconds. So we use the idea of a Gaussian process regression to generate our emulator. So the Gaussian process regression is a non-parametric regression method which enables us to interpolate between existing simulation data and construct a power spectrum emulator which can predict the data at n sim points. So I'm not going to great details into the GP, but the key idea is that the Gaussian process assumes a multivariate Gaussian distribution of the data. So the advantage of this is that at the point where you don't have a lot of training data, it can capture the uncertainty by this distribution. So you know that when you don't have enough data at certain point in the parameter space, you will see a larger uncertainty from the outputs. So this is the plot that I already showed in the previous slides, but this time we plot the true value from the simulation against the predicted value from the emulator. And you can see that in both cases, we're able to generate the spectra from the emulator that looks very much like the simulation results to within a few % of error. And finally, with the emulator, we can do something that the simulations cannot do. For example, here we're able to actually explore this three-dimensional parameter space and see how simultaneously varying these parameters will change your constraint on the reionization. So here I simultaneously vary the three reionization history parameters, and you can see that the constraint can vary depending on which parameter set you choose. So this concludes our work. So we first introduced our semi-numerical code Ember for simulating the EOR in large scales. And then we calibrate Ember against the radiative transfer hydrodynamic simulation scores and see that they look close to each other in terms of the observables. And then we go on to see how the EOR parameters can change the KZ signal by varying those parameters in Ember and produce the angular power spectra. And finally, we build an emulator with the simulation results, and we show that we're able to recover the simulation results pretty well with our emulator, and this can potentially allow us to carry out full parameter space study and likelihood analysis for future observations. So I want to mention that this is still work in progress, so stay tuned and for those papers that's coming up in the next few months. Thank you. I stop here and take any questions you have.
Thank you very much. Any questions? So there's one from Gabriela. What are the main differences between Amber and 21 centimeter fast?
Let me go to the previous slides. So we use pretty different method to carry out the simulation. So the 21 centimeter fast is also kind of based on this excursion set formalism, and but the for example, it uses the photon escape fraction to calculate those ionized bubbles by gradually expanding the ionized regions and see at each point whether a point is ionized. And here we use a completely different approach. Oh, sorry, I go to the correct slides. And here for Ember, the main idea is to use abundance matching to be able to generate the reionization redshift field. And also the parameter settings are very different. So in 21 centimeter fast, you do not have direct control over the reionization history because you only have, for example, parameters like the mean halo. Well, the mean halo mass is similar, but you control, for example, the escape fraction. In our case, our input parameters are the reionization history parameters. So we got direct control over these parameters, and we can separate the degeneracy between them.
Okay, thank you. I got just one quick question. You shown some scaling of the amplitude versus delta Z or Z reionization. How do they compare to the other simulations, like in SHOW and Battaglia? Did you have a look?
Yes. So here I didn't, in this plot, I didn't overplot our relation with previous works. This is partially because we're still thinking about like the most accurate way of comparing them because the nature of the simulations are really different. And for example, for the Battaglia 2013 paper, they also have a scaling relation here, but there, I think they, for example, when they vary the duration, they didn't control the mean free path, so there's kind of a degeneracy between the two. So that can lead to some difference in this scaling relation. And also note that our duration definition is actually different from previous works in that we have like a longer extension of reionization from 5% to 95%. So we also need to calibrate on that before we can do justice in the comparison.
Okay, thank you. And a new question, just fast. How fast is Amber as compared to excursion set based model? For example, to run your 2 gigaparsec simulation, how much time did you take?
So for the 2 GPC box, it takes, let's say, a few hours, likely less than 10 hours. And then if you run a 1 GPC box, it only take a little more than an hour on a single computer.
Okay. Thank you. Thanks for the questions and answers. More on the Slack if you want. Let's move on to the next talk. Simone Ferraro.
Yeah, hi, I'm here. Let me share my screen.
On detecting patchy reionization in the small scale CMB.
All right, great. Can you see the slides?
Yeah, perfect.
Okay, awesome. Yeah, so thank you very much for the invitation. Today, I'd like to talk about some new techniques to detect KZ on small scale CMB, particularly KZ from reionization. So these mostly work based on a couple of papers I had with Kendrick Smith, and also some more recent work with a number of collaborators that are listed here, and I'll go in details. All right, so I know there's been sort of many introductions to KZ, so I will keep this very short. But I really like this picture, and I just really want to note that the CMB experiments, sort of the new generation of high resolution, low noise CMB experiments, will really provide a super useful probe of the low redshift universe as well, simply because the CMB photons have to go through the whole observable universe kind of by definition, right? And we know that they interact with the low redshift universe, both through scattering and through gravitational effects. So effectively, new high resolution CMB maps are large scale structure maps as well, and they can be used in sort of many applications, and this is becoming very exciting. All right, so as we've heard before, KZ is kinematic Sunyaev-Zeldovich effect is created whenever whenever you have electrons that are moving in the cosmic velocity flows. And we know electrons do Thomson scattering to CMB photons, and whenever they Thomson scatter, these electrons pick up a Doppler shift due to their peculiar motion. So very simply, you know, the KZ effect is given by, is proportional to the column density of electrons times Thomson cross section, which is essentially the probability of scattering. And if you do scatter, if a photon does scatter, so non-relativistic limit, the Doppler shift it acquires is just V over C. So this, this formula has a very intuitive explanation. All right, so it's really the product of column density of electrons. So it's some probe of astrophysics times the radial velocity, which is a probe of cosmology. And in all, you know, all I will say, I will assume we know. So we're working within lambda CDM, so we know the statistical properties of the velocity fields at all ratios. All right, so how does this work for reionization? Well, we've heard many times before. You have these ionized bubbles, and of course, inside the bubble, the gas is predominantly ionized, so it will Thomson scatter CMB photons. Outside is a neutral medium, so there's no scattering. And you know, we just updated this formula where now the KZ from reionization is given by column density of electrons in the bubble times the velocity of the bubble, essentially the radial velocity of the bubble. All right, and so here is what it looks like in some simulation by Nick Battaglia and collaborators. So you know, the sort of large scale fluctuations here, hot and cold spots are due to primary CMB, and that kind of small scale granularity is this kind of bubbles. You know, you're really seeing the bubbles moving away or towards us, and that causes the signal on small scales. All right. As you all know, also there's another source of KZ, which is the one from that we detect directly. Now there's you know, a lot of papers that detect late time KZ. Is the one created by galaxies and clusters. And at the power spectrum level, you know, you know, they're both uncertain, kind of a de facto of two, I would argue. But at the power spectrum level, they both look fairly featureless, and you know, depending on the simulation, you know, there's a bit of scatter, but they all look, you know, fairly featureless, fairly similar, and with similar amplitude. Okay, so you know, isolating. And moreover, I should say, you know, they are degenerate with foregrounds as well, as we've heard, right? There are other foregrounds such as TSZ, CIB, etc. Right? So while it's possible, and certainly people do put upper bounds on the size of the reionization KSZ, really getting to sort of the common wisdom until so fairly recently was really getting a very, very precise measurement of the reionization KSZ power spectrum only. So just the reionization part would be sort of challenging once you marginalize the uncertainty on the late time component as well as other foregrounds. So you know, we really asked the question, you know, can we isolate the reionization part from the late time KZ? And we'll come to foregrounds later. Let me just start with just separating the reionization KZ. So these two lines, the red and the green line on this plot. So as I said, it's a challenging measurement because they are very degenerate at power spectrum level and degenerate with the other foregrounds. But yeah, Kendrick and I claim the answer is yes, we can isolate them, and we proposed a method based, which I will explain based on these two papers. Okay, so the idea is rather simple. So let's look at you know, you've seen this formula at the top before. The KZ power spectrum is usually just given by an integral along the line of sight of the sort of RMS velocity, and here I'm really talking about the sky average KZ power spectrum. So what enters here is sort of the sky average velocity dispersion times the power spectrum of the electrons. Okay, but now let's really look on a particular line of sight. For example, this one, the top one, right? So then you see that if I look at the small scale power spectrum, really just imagine a 1 degree by 1 degree patch or something, right? And on a 1 degree by 1 degree, I can measure the really high L power spectrum just there locally, right? In that case, you know, the integral won't be the sky average of the velocity, but it will just be the actual realization of the velocity on that line of sight, right? If I take another line of sight, you know, now my local KZ power spectrum, the local value of the KZ power spectrum will be given by, you know, the realization of the velocity on this other line of sight, right? And since realization of velocities are different, you know, between different lines of sight, it means that you do have fluctuations from point to point in the sky of the small scale amplitude of the KZ. So you see where we are going. We're going to try to measure some sort of non-Gaussian statistics of the KZ, and in particular, we'll claim that this non-Gaussianity is actually really large. Okay, and to see this, let me say, to see this is let's you know, take this toy model. So we can divide the line of sight to reionization. The length is about, you know, 10 gigaparsec in you know, segments which are of length of roughly the Courant velocity, the Courant length of the velocity field, which is about you know, 50 to 100 megaparsec. Okay, so let's say we have about 200 pockets of independent velocity between us and reionization. Then you know, this integral will vary by order, you know, root 2 over n, where n is the number of independent velocity realizations, or about 10%. Okay, so the claim here is that if you go and look at, you know, two different parts of the sky, you know, the KZ amplitude from reionization will vary about 10%. Okay, so this is really large amount of non-Gaussianity, right? You know, if you just think, you know, our current measurements of FNL sort of order 5, that's a 5 times 10 to the minus 5 in terms of non-Gaussianity, right? So it's 10% is a very large amount, and in fact, it's the largest CMB non-Gaussianity in the high L temperature, and it's in fact larger than all the other foregrounds. So that's what makes it sort of easier to extract. Okay, so this is so we saw that by looking at this non-Gaussianity, the variation of the signal across on different sight lines, we can detect the KZ. But the next question is, can we distinguish? Does this allow us to distinguish the reionization from the late time component? And the answer is yes, and that's simply because now we can use the velocity covariance length, which is about 50 megaparsec, as a standard ruler. Okay, so if you're seeing modulation by the velocity field at reionization, you see those modulations on very, you know, you put the ruler very far away from you at about 10 gigaparsec distance, right? You see this ruler that subtends a small angular scale. While if you put this ruler closer to you at late time, where, you know, galaxies and clusters sort of dominate the KZ effect, then you will see this modulation on larger angular scales. Okay, so you really look for the modulation of the power spectrum, and the modulations on small scales will tell you, you know, the KZ from reionization. The modulation on large scales give you the KZ from late time. And in particular, if you want to get rid of, you know, marginalize over the an unknown amplitude of the late time KZ, you can just marginalize over slow variations in the power spectrum. So this can be sort of formalized mathematically, and of course, in the time available, I won't do full justice to it. But you know, all the math is in these two papers. Here, let me just show you with a simple example. Let's imagine we have a delta function source of KZ fluctuations as some Z star. Okay, so DCL DZ is a delta function at peak to Z star, and let's look at how this quantity, which is the power spectrum of the small scale power spectrum. So, you know, we really measuring the KZ power spectrum in a lot of different patches in the sky, and we're taking the power spectrum of that field. So is this CLKK, where essentially K is some square of the temperature appropriately filtered, and by, you know, once you have this quantity, this is something you can measure from. In fact, it's rather easy to measure from your CMB maps. Now, if you put a delta function source of KZ at Z star, if you put it at the reionization like Z star of 8, you get this green curve, right, with peaks at L of 150 or so, while the late time KZ peaks at L about 40. Okay, because this is simply because of the very different distance from the galaxies that are source of KZ or reionization. Okay, but the really cool thing is that the shape of this, so the amplitude, the astrophysics has now gone completely into the amplitude of this curve, because the shape is completely determined by the velocity correlation function, which both at late time and reionization is linear theory is a very good approximation. So the shape of this curve is we know that there's very little uncertainty. We know it to percent level if we assume lambda CDM cosmology. Okay, so and now we can marginalize over sort of the late time component and get the reionization component only. So that's the game. That's the game we're playing. And then there's the next step. Let's say we have isolated the reionization, and now and then I claim we can do this in kind of almost model independent way, because of the shape is completely determined by a linear theory cosmology. And all the astrophysics has gone into the amplitude of this of the reionization component, for example. So then we go and we play the games that sort of we've heard before a lot, which once we separated it, the shape of and amplitude of the KZ power spectrum gives us also physical parameters of reionization. So here again, going back to the simulations by Nick and others on this call, we know that, for example, a smaller tau leads to a smaller KZ power spectrum. So if you keep the template fixed and you just move it up and down in redshift, all you're doing is you move the KZ power spectrum up and down. There's a very good reason for that I'll come to in a moment. But you're sensitive to things like also duration of reionization. So for example, for a longer reionization, you get more power, you get small bubbles at high redshift. At high redshift, you have larger density of electrons simply because the universe is kind of smaller, right? So and that enhances the high L power compared to the low L power, and vice versa. If you have a smaller a shorter duration, you enhance the low L power compared to the high L power. Okay, so now the larger tau gives you larger KZ, for example, and the shape sort of depends on the reionization history. And we've heard several talks about how you can even improve over this parameterization. And certainly, what I want to say though is something that I don't think is sort of widely appreciated, is that the scaling with tau is rather robust, and that's because in fact you can even sort of analytically derive the scaling with tau, and that's because the physics is very simple. So let's assume the KZ. Yeah, sorry.
1 minute.
Yeah, okay. I'm almost there, right? So the KZ fluctuations. Okay, maybe then I'll skip this. I'll skip this part. But let me just say that the physical number density of electrons, right, is the kind of moving number density which is known times 1 plus z cubed, right? So the z here plays really like a clock, right? The size of the fluctuations are proportional to 1 plus z cubed. So you can even derive the scaling kind of analytically, and there's not much that you can do to break that. So that's rather robust. Okay, so let me sort of sum up. So in blue here, you see the sort of KZ constraints you get from this 4-point function that we talked about. So you see, maybe it's not enough to fully constrain the break this degeneracy between the tau and duration. However, we can do something else, which we can put back the 2-point function into play. And now the 2-point function, you do need to marginalize over quite a large uncertainty on the late time KZ. So we do that indeed, right? So even the 2-point function now loses most of the constraining power. However, they have very different sensitivity to the duration versus tau, because essentially, you know, the 4-point function is non-Gaussianity, and the longer reionization is, the more Gaussian the signal becomes. So you do have very different sensitivity than the 2-point function. So once you combine them, even if you have now on the 2-point function, you have a very broad prior on the amplitude of foregrounds or late time component. Now, when you combine the two, you do get you do end up with constraints that are kind of independent of foregrounds or astrophysical uncertainties, and they are rather good. Like they're you know, comparable with the sort of cosmic variance limit on tau that you can get from a future space-based experiment, for example. All right, so I'll stop there and be happy to take questions. Thank you.
Thank you very much. So quick question, there's a question on the chat. How much the shape or peak of the CLKK changes with the reionization curve due to the dependence of the halo masses driving reionization?
Oh, so this shape does not at all, because it's really just you know, it's really just this modulation done by the velocity field that determines the shape of this. I'm not sure if I understand the question correctly, but it's what we are going to do is like use the amplitude of this say reionization part is what contains the astrophysical information, and that is what so contains information about the mass, for example, of the halos. And then it is true that sort of in this simple parameterization, you know, you can't sort of distinguish, you know, exactly how you got a bigger tau or how you got sort of a longer duration of reionization. For example, you would have to map, but this is just a simple, you know, parameterization, and we could go back to, you know, if we have simulations with different masses, we can take the derivatives, we can absolutely sort of see what constraints on some halo mass you can get from this. I just don't know off the top of my head, but you know, there's these two steps that are separate. One is we isolate the reionization component, and then how you interpret the, you know, amplitude of the reionization component is a sort of different game. But yeah.
Sorry, we have to move on if we want to finish. Not too far away. I encourage you to continue discussing on the Slack between the questions and your answers. Thank you very much, Simone. We can now move to the last talk of Chen Henrik on reionization effective likelihood code from Planck final data. Hello.
Hello. Yes.
Yep.
Can you see everything?
Yeah, sure.
Okay, great. So
we see that. Sorry, we see the two slides, the current one and the next one as well. So
okay.
Switch between the two screens.
I see. How about right now? Do you see just one slide?
And we see a gray area without nothing.
Okay. How about now?
We see the we see the slide, but with the.
You have the slideshow on the side, but well,
yeah,
probably just have to deal with that. Okay. Great.
Thanks.
Yeah. So yeah, thanks so much everybody for having me here. Yeah, great pleasure to be able to talk here. My name is Chen Henrik. I'm a postdoc at the California Institute of Technology. I'll be talking to you today about a recent code release and a paper that will actually appear in 6 hours on the archive tonight, called Reionization Effective Likelihood from Planck 2018 data. This is work done in collaboration with Wayne Hu at University of Chicago. Just give you a little brief overview of what we're going to talk about today first, before delving into the details. You know, this is my 1-minute summary up front. We're using a principal component analysis to look at, so we've heard about KSZ, which mostly on small scales. This is going to be about the large scale E-mode polarization data. And the principal component analysis allows you to basically analyzes all the possible ionization histories and constrain them in the way such that you can actually compress it into an effective likelihood code. So this is the first time we release this code that allows you to do a very simple, allows you to do model testing of ionization history in the very simple way. You know, don't have to modified CAM, don't have the hookup Planck likelihood and things like that. So no need to get your hand dirty that way, but you can get constraint results very quickly. Also enables fast and consistent joint analysis in the way that I'll elaborate on more later on, but basically, typically people have been taking a tau prior when they do joint constraints or looking at model some more generic classes of models for doing constraints for doing the joint analysis with say KSZ or 21 centimeter or other kind of reionization data. But here, because of this code, you can now do a more consistent analysis, forward modeling everything at the ionization history level consistently. And at the end, I'll briefly mention some model independent constraints that we got from PCs as well that differ slightly from what we have from Planck, which will be important to take note. So let me get started on the just a bit of the principal component background. So, this is the CLEE large scale reionization bump. It's caused by the scattering of the temperature quadrupole with free electrons during the epoch of reionization. So notice that this bump can have various heights or shape depending on how reionization happened. Typically, we're using a standard step-like say Tench function to parameterize the effect, at least in the CMB CLE CL data analysis. However, there's more information you can get from the shape of this bump rather than this just rough height and location. So what we're going to do that instead of using the simple step function to parameterize the global ionization fraction, we are going to use the principal component analysis where you assume, first of all, a fiducial model. It can be really anything. So we assume it's 0 beyond some Zmax and then, fully ionized below some redshift of 6, and then some just a constant in between. And then I should say, this is not news. This is developed in 2003, actually by Wayne Hu and Gil Holder. So this was their pioneering work for this this analysis. You basically pick a fiducial model and then perturb around the fiducial model to get a Fisher matrix that looks at the response of the data of CLEE as a function of all your observable CLEE as a function of ionization in the particular redshifts. You do the diagonalization, you get the eigenfunction of the Fisher matrix as your principal component that I will denote here as SA. This is what they look like. So the first, notice that they sort of just wiggle more and more after you rank them by inverse variance, so that the first ones have the most contribution to observables. So it's so the first two modes basically describe sort of a total tau with the first one with the more emphasis at the higher redshift, and then the second mode sort of lets you trade the high redshift versus low redshift ionization. And this is what they look like in terms of the cumulative optical depth. So obviously the first two modes have the most contributions and the other ones have less. So just to convince you that this works, you can basically only 5 PCs are needed to describe CLE fully to cosmic variance. So this will be valid for future CMB large scale data as well, such as those who have from class or Liebert. So I just want to show you, for a simple Tench model, you can use 1 PC to describe. You can use 5 PCs to describe its impact on CLE. So going from 1 to 3 to 4 to 5, you see that everything matches to better than cosmic variance. And this applies not just for Tench, but for all the models that you can think of that's between 6 and 30. And of course, you can generalize the approach to extended range of redshifts as well. Okay, so now I just want to show you Also, briefly what this looked like in 2018 data. So let's do an MCMC instead of having the 5 lambda CDM parameters plus tau, which usually just corresponds to when tanh starts to step up. We're going to replace tau by this M1 to M5, this 5 PC amplitude that we use to parameterize a general XZ of Z. In particular, all 95 PCs, we have 95 in our formalism, would fully describe XZ of Z, but we only need 5 to actually describe the observable impact on CLEE. So we only keep 5 of them. And this is what they look like in a triangle plot. I plotted out the 2015 version as well, where there was actually a hint of higher redshift ionization, as well as contributing to a bigger value of tau. But so now a lot of that has gone down, and so we go from this red to blue contours here. Yeah. And so just blowing it up, because M1 and 2 are the best constrained plane, shows you a bit of the evolution from 15 to 18. And in particular, we're actually not using the full legacy data from Planck. We are swapping the low LEE likelihood to use the more updated one in 2019 called SRO2, which has a better foreground cleaning, and that further shifted tau a little bit to the higher end. But so that's our blue contour here, and we have priors on those M's that will not enter our RELIKE code, as I will describe why, but they will be useful for model independent constraint. Okay, so just a quick summary of what this code is about. Well, now that I got this constraint on this thing, all of this box edge encloses all the physical models, meaning XE is a fraction, it's between 0 and 1 with a helium contribution. And so you can see that the black curve here, it's the tanh model. It's really only one part of this entire physical space that's allowed. And then furthermore, the data constrains you to this ellipse area that data is able to constraint. So we're turning all of that, not just with the tanh model, into effective likelihood code, where you can basically pick any models of ionization XZ of Z, taking in some model parameters. So for tanh, it's just going to be tau or whether the redshift of transition is. Project this XZ of Z onto the PCs to get its amplitude, get the decomposition. And then what we do is we use kernel density estimates to go over all the PC chains we have with the Gaussian kernel, mean 0, covariance being a fraction of the chain covariance, and basically go over the chain to get you the likelihood of your particular data. It turns out that the Gaussian approximation is also very good. So if you see these ellipses that are dotted, these are just assuming a Gaussian likelihood in the M's using the chain covariance. They're also pretty good. So we're going to offer these 2 modes in our code, and then from this, assuming a flat prior on your model parameters, you can easily get the posterior of your model very quickly. So we have this code available on GitHub. I just made pip install RELIKE work like last night, so you guys are free to download it and check it out. But there'll be more README and notebook tutorials on the actual GitHub. You can hook this to an MCMC sampler and do joint analysis very easily. We actually released the version we use that's hooked already with Cosmo MC with a Fortran implementation of RELIKE. And that's also at this link. You'll be able to download and play with that if you want to. Python package has only the Gaussian mode, while the Cosmo MC version has both. But as I'll show, they actually work both pretty well in terms of the reproducing results from an exact MCMC with the full likelihood code. I took some screenshots of the Jupyter notebook, but probably it's not necessary. I just wanted to sort of show you, how easy it is to just, define a function and then, define a function right here, and you just get the values for the MJ and you can get a log likelihood very easily. We normalize it to the best fit tench model in Planck, so you can have a feel of how good your model fits immediately. And plotting a posterior for tench takes less than 1 second. In a Jupyter notebook instead of running MCMC for 24 hours. Okay, I'm not sure how long I have left, but I'm happy to show just a few examples of what we tested that it works.
Let's say 1-2 minutes so that we don't.
Okay, that's perfect. Yes, perfect. Okay. Yeah, so here's we test the code with the tench model, and so pink is the exact where we actually went to modify camp, putting in the actually camp had already had tench, but in the next example, we'll have to sort of modify the XE of Z function and hook it to Planck likelihoods. That's the pink. That takes like 24 hours to run on a node with 8 cores on the cluster. KDE and Gaussian, they reproduce it pretty well, and just note that the Gaussian, earlier just took 1 second. If you want to run the MCMC, it's gonna take 5 to 10 minutes to converge. It's really, really fast. And then we also plot the cumulative optical depth. It's technically 0 over here, but because of the PC, we truncated at 5 PC. There's a bit of oscillation that can only be restored with higher PCs, but this is not really a problem, just something to keep in mind. That's why it has those oscillations. The second step is more interesting. So the second example is more interesting. So this is a 2-step model where we keep the tench, but sort of allows for ionization plateau at high redshifts. And if you do a exact MCMC, these are the red contours over here, and the KDE and Gaussian node of our effective likelihoods both work pretty well, as you can see. And here I indicate the best fit model and the 95% confidence level model that is shown on this plot. You can do the same thing with tau cumulative and the posterior. So let's focus on the right panel first. This is showing how exact and KDE and Gaussian all agree very well once again. What's interesting to note is that if the tench posterior for total tau was at blue, and the 2-step is this dashed, and the reason is because we allow for higher redshift ionization, and it sort of is able to contribute. Data allows that, and so it contributes to this difference. What is very interesting also is that our model-independent PC results, and now we're going to put the prior on physical models, priors to eliminate on physical models, and we get pretty much the same posterior. What is interesting is the Planck 2018 cosmological parameter paper used another model-independent method called FlexNOT, which is in principle model, capture a lot of models, but they had upper limits on the cumulative tau between 15 and 30, which that is 3 times lower, more stringent than ours. So we actually have an upper bound that is about 3 times greater. Just to make sure everything's all right, we looked at the specific 2-step model, without using the PC, just the exact likelihood, and get the 0.014, something that is much closer to our PC analysis. Just checking that what we're doing still makes sense. You could also and then we can also change the Zmax from 30 to 50, showing that all results are consistent with each other. There's and then also, if we're worried about putting the prior, this is directly showing what happens when you impose the prior and not imposing the prior. The upper limits barely change, and the effect of imposing the prior is really just to remove some of the negative ionization here. That is, not really a physical model. So in conclusion, we compress this, plug 2018 data into an effective likelihood and obtain model independent results. And so now code is public and you can use it to really help you with model testing. So I'm thinking, when previously a speaker was mentioning how KSZ and analyzing high L and low L data, sometimes we don't have the same analyzation model. Well, now you can do it consistently with this code. So I'm really looking forward to talking with you guys. Maybe after the talk during this conference about Slack, about the various ways you can use this. I know there are many samplers out there like Kobaya, Cosmosis, 21 centimeter MC, and Cosmo Rai MC, and all that. So a lot of you are doing really cool work with the joint analysis, and I think this is where the future will go for our future directions for our field as well. So I'm super excited to be able to be part of that and talk with you more. So yeah, let me know if you have any questions as well.
Thank you very much. There's one question about, okay, well, do you have an idea why the Planck constraints on high redshift tau is so low compared to use? Why is it 0.07 instead of 0.020? Do you have any hint about why?
Yeah, so so this is FlexNode. So first of all, let me tell you what the FlexNode method is. It's actually using a few knots in redshift space and varying the amplitude and the position of these knots in redshift space for parameterizing ionization fraction. And then I think they vary up to like 5 knots. So in principle, it's general enough, but we think that, just the way that the priors are imposed, there's either implicit or explicit prior assumptions that goes in there that may have affected this particular constraint here. And I think that yeah, if you are comparing your model, it's you want to be careful with yeah, comparing it directly on the XZ of Z kind of constraints, because a lot of times those have prior assumptions that are specific prior assumptions, and sometimes limited to a set of models. Maybe it's not general enough. So anyways, we have made yeah, the really right way to do is using the relike, which give you the right likelihood for your particular model. And we have tested, at least with a simple toy model, without using any PC, that our results are consistent with that. So I cannot really further comment because yeah, I do not know exactly the details of their analysis.
Thank you. Okay, we have to stop at some point, so we're a bit late already. Thank you very much, all of you, for this. Well, I would keep saying afternoon because it's evening for us, but whatever time. Thanks everyone. We will have a new session tomorrow, and I will give you it starts at 11 UTC, and we will have 2 sessions of 3 talks each, and concluding remarks at the end. So again, feel free to send subjects you want to be discussed at the end of the day tomorrow, and continue asking questions and discussing on Slack if you want. So I think I'm almost done for what I have to say. Did I forget anything about the day? Okay, so thank you everyone.
I think so.
Talk to you tomorrow, and on the new Zoom link, which is provided on the Slack as well, and on the email. Bye bye. See you tomorrow.
Bye. Have a good day.
Bye. Thank you.
Let's closing this Q&A. Okay. Should I be the one closing the? Adeli, do you want to stop the recording, or it just stops? There's something to do for the recording?
It's a good idea. I need to do it.
Okay.
Okay, and the live.